Chapter 17, Quantum Vibration. Section 17.3, Quantum Vibration of Polyatomic Molecules. A polyatomic molecule contains 3 or more atoms. In general, if a molecule contains n atoms, it has 3n atomic coordinates, because each atom has 3 coordinates x, y, and z. So this molecule has 3n atomic coordinates, and thereby 3n independent motions, because each atom has 3 independent motions in the x, y, and z directions. Now let's look at nonlinear molecules versus linear molecules. A nonlinear molecule has 3 translational modes in the x, y, z directions, and also 3 rotational modes about the x, y, and z axis. So for example, if you have a water molecule, let's say this is the z-axis, and then we can draw another x-axis and then another y-axis perpendicular to the screen. So 3 rotational axes, 3 rotational motions. And we know in total there should be 3n motions. So 3n minus 3 translations minus 3 rotations. Well, a nonlinear molecule should have 3n minus 6 vibrational modes. For example, water. Water consists of 3 atoms. 3 times 3, we have 9 motions. 9 motions minus 3 translations minus 3 rotations, we have 3 vibrations. And you are looking at the 3 vibrations. This is the so-called anti-symmetric stretching, because over here, when this bond is stretched, this bond is compressed. They are opposite to each other. Over here, it's symmetric stretching. Both bonds are stretched or compressed at the same time. There's another scissoring bending. So you can call this bending as well. We're just changing the bond angle here. All 3 are vibrational modes of water. Now let's look at a linear molecule. If you have a linear molecule, still there are 3 translational motions, but only 2 rotational motions, because there are only 2 rotational axes. Let's look at CO2 as an example. Again, this CO2 may rotate about 2 of the 3 rotational axes. The last one, the molecular axis, does not count. This CO2 does not rotate about its own molecular axis. And therefore, if you have a linear molecule, again, the molecular axis does not count. So you have only 2 rotational axes or 2 rotational modes. And because of that, we use 3n minus 3 translation minus 2 rotation. We have 3n minus 5 vibrational modes, 1 more than the number of vibration modes of a nonlinear molecule. So now let's look at CO2. CO2 has 3 atoms, therefore 9 motions minus 3 translations, 2 rotations. We have 4 vibrational modes. We have symmetric stretching, anti-symmetric stretching, and we have 2 bending motions. In these 2 vibrations, the bond angle, OCO bond angle, changes, but they are changing in different planes. So one is on this plane, the plane of the screen, and this motion is actually taking place in a plane perpendicular to the screen. Alright, I have to let you imagine this is actually a 3-dimensional animation, and the CO2 bending takes place on a plane that is perpendicular to the surface of the screen. This one is just in the screen. Again, this is the just the water molecule of 3 atoms and 9 motions. Minus 3 translations, minus 3 rotations, we have 3 vibrations. Anti-symmetric stretching, symmetric stretching, and bending. So bending is somewhere here. All these are bending, and then we have stretching here. I think anti-symmetric stretching has a slightly larger wave number than symmetric stretching over here. Yeah, the numbers are here. This is slightly larger than this, and we have scissoring bending over here. Those are the wave numbers from the NIST website. But if you really look at this infrared spectrum of water, you can see it's not as clean as we expected. We see a lot more than 3 peaks. So why so many peaks over here? Well, I just want to remind you, other than the vibrational motion, a water molecule may have rotational motions. So a water molecule may absorb a photon with energy to excite its vibration and also its rotation. And even more complicated, a water molecule might be in the rotational excited energy level in the first place. And when such a water molecule absorbs a photon, well, it can be vibrational excited and rotational de-excited at the same time. So that's why we have all different kind of situations regarding the rotational excitation or rotational de-excitation accompanying the vibrational transition. That's why the infrared spectrum of just water vapor can look so complicated with many peaks. But all this corresponds to the vibrational excitation of the bending mode. And I think of this correspond to the symmetric stretching, and of this correspond to the anti-symmetric stretching. Why so many peaks? Well, the vibrational transition is accompanied by rotational excitation or rotational de-excitation.